How is everybody?
Good,
Nice.
sir.
Good, sir.
Okay, so according to our calendar, we have just about one more month left in this class. Okay, so in that 1 month, but in that 1 month, we'll be covering Schrodinger equation for a free particle, and by the end of this month, hopefully you should be in a place where you can read more advanced textbooks on quantum mechanics, which introduce you to other solutions of the Schrodinger equation. Okay, all right. So good morning, guys. Welcome to our 26th online class. We have about one more month left in this class, and the hope is that by the end of this course, you should be in a position where you feel comfortable reading, if you want, if that is your interest, to read more advanced textbooks on quantum theory, and that wherever you might encounter some applications of quantum mechanics, you are able to read about that and discuss that in an intelligent manner, right? Of course, because at the end of the day, most of you, I think it is maybe unlikely that you want to be like theoretical physicists. So perhaps your interest is more in wanting to understand, get a basic idea of what quantum mechanics is, because it's a fundamental part of most of our technologies today. And so I've tried to structure this course in that manner. And so over the next 1 month, we'll have one more quiz, and then I plan on giving you 2 more homework sets. And I realize that I'm very far behind in correcting your 3rd homework set and the midterm. So I plan on doing that over the coming week. And so let's have a bit of a recap of the things we have done so far. Okay, just to get an idea of all the ground we have covered. So you can see. So these are all the pages of notes from class, right? And we are on page 96. So I guess that's a lot of material we have covered. At least it seems that way. And I think by now you all have a very strong basic understanding of complex vector spaces, operators on these vector spaces, the representation of and then how to combine these vector spaces to get bigger ones, which are called through tensor product operation. And through the tensor product operation, you combine different systems to get bigger systems. And that allows you to understand things such as entanglement, which is one of the most fundamental aspects of quantum mechanics. And then we have, of course, the uncertainty principle. And the uncertainty principle, as we have explained it in terms of expectation values of operators. And we derive the uncertainty principle in a very general way for any two operators which don't commute with each other. So if two operators don't commute their expectation values, so here delta A is the uncertainty in the expectation value. Their expectation, the uncertainties will always obey this relationship. So we will see later that when you translate this into, when you start talk about a continuous Hilbert space, such as that of a particle on a free particle on a line, then, for example, one of these will become the position, the other will become the momentum uncertainty, and we'll get our usual Heisenberg principle. And then, of course, I would also hope that by now you have a decent understanding of the process of measurement and collapse. And again, we have tried to talk about the tools which are necessary for performing measurement. So in terms of operators, right, then we talked about the transition to continuous degrees of freedom. And so what happens is that we go from a finite Hilbert space to an infinite dimensional Hilbert space. But again, that is nothing to be scared of. An infinite dimensional vector space or a Hilbert space is still a vector space. So it has all the usual behaviors. It has all the usual behaviors of any vector space. All right. So all of this was, a while back, I guess. Then I talked about this block representation of quantum states in terms of points on a sphere. Again, this is very, very useful when you talk about something like quantum computation, and we will have a brief glimpse of quantum computation in the remaining classes. What else? Then I introduced the basic notion of a particle which is trapped in a box and how one experimentally implements this. And then I talked about, I showed you the form of the Schrodinger equation. Then now the thing is that this concept of the Hamiltonian is something that we get from classical mechanics. But because of its somewhat more abstract nature, I will not be going into the classical mechanics origin of what a Hamiltonian is, okay? So you will have to sort of just be happy with this definition of the Hamiltonian, that it is the kinetic plus potential energy of our system, okay? And then so using this, so then we have the formal definition of this Schrodinger equation. And I did a sort of a hand wavy derivation of the solution of the Schrodinger equation. And for let's see, this was the mid-sem review. For the case of a particle in a magnetic field, we did the derivation of the time evolution of this field, and that time evolution involves taking exponentials of this operator, and I showed you how to take these exponentials by expanding the function as a Taylor series and then collecting all the various terms And it's not very difficult once you realize that the exponential, for instance, the Taylor series involves repeated powers of sigma z. And once you see that sigma z, when you repeat powers of sigma z, the same terms repeat again and again. And so you basically get two sets of terms. One set of terms corresponds to a cosine, the other set of terms corresponds to a sine, and we get this sort of a behavior for the coefficients of our quantum state. The coefficients behave as oscillating functions of time. And okay, so now, and then in yesterday's class, I tried to go into a little bit more depth because of where that Hamiltonian comes from with the dipole moment. And but I don't know how successful I was. So in any case, that is something that you can find, for example, in first year physics textbooks such as Kenneth Crane. So I would refer you to that book. Okay, so are there any questions at this point? Okay, so today what I will do is I will derive the Schrodinger equation. Okay, so there is a very simple and straightforward derivation, and it's also given in Barak-Shoshani's notes. So I'm going to follow that. Okay, and this doesn't involve really any assumptions, and that's why it, I think it's really nice. So that is our goal for the day, to derive the Schrodinger equation. Okay, and it's important to remember that when I say derive the Schrodinger equation, I am referring to the Schrodinger equation in this form, that H psi is equal to what is it? I H bar d by dt of psi. This is what I mean by the Schrodinger equation. What you're familiar with is, well, that you have encountered in previous classes, I guess, is this form of the Schrodinger equation, minus h bar square by 2m del square psi plus v something xt psi is equal to e psi. This is what you have encountered, I think. This is the time independent Schrodinger equation for a free particle. Well, not only for a free particle, but for a single particle. Okay, well, not only for a single particle, it's a time independent Schrodinger equation. But the most important difference between these two is that A and B, A is very general. It applies to all systems, whether they are continuous or discrete. Because it does not tell us, that. So, and whereas B only applies to systems that are continuous. That is because of the presence of this gradient operator, right? So the gradient operator means that there is some, that psi is some function of x, and if psi is a function of x, then it's a continuous system. Okay. All right. So now we are going to derive the version A. Okay. So now, as I've explained to you before, how does time evolution happen in a quantum system? Time evolution happens due to the action of certain operators which are called unitary operators. So if I have a state psi at a certain time t1, and I want to ask what happens to this state such that it becomes a different state at a time t2. So the way, well, all states transform within between each other using operators, right? So there has to be some operator which takes the first state and gives us the second state. So this operator will be some function of t2 and t1, right? Now, the requirement of conservation of probability, what is that? That is the statement that the length of this vector should remain the same. This requirement tells us that this operator has to be a unitary operator, which means that its inverse is equal to its Hermitian conjugate. Okay. All right. Now, if you look at this expression 1, and we set t1 to be equal to t2. Okay. So in that case, what do we have? We have u of t1, right? And this has to be equal to the identity operator, right? Because in that case, psi t2 and psi t1 are the same. So by definition, this has to be equal to the identity operator. And so basically, if nothing happens, then, well, nothing happens, and nothing happening is described by the action of the identity operator. Okay. Now, on the other hand, let us say that we have a sequence of 3 times psi t1, t2, and t3. Okay, so we have the state at a time t1, the state at a time t2, and the state at a time t3. Okay, now to go from t2 to t1, as per our expression, right, it will be some unitary operator, and this unitary operator will be some function of t2 and t1. And similarly, to go from t2 to t3 will be some unitary operator, or the same unitary operator but written as a function of t3 and t2 instead, right? But you can see that instead of going from t1 to t2 and t2 to t3, we can go directly from t2 to t3. Okay, if we do that, then this becomes u of t3 t1, right? So what will happen is, we can write it like this: psi t3 is equal to u t3 t2 psi t2, and psi of t2 is equal to u of t2 t1 psi t1, right? And but this whole thing is equal to u of t3 t1 psi t1. So since this expression and this expression, they are equal to each other, this implies that u of t3 t1 is equal to u of t3 t2 times u of t2 t1. Okay, I hope this is clear. It's very, I mean, it's you know, the most obvious thing that can happen, right? Okay, now, so we have this unitary operator and it satisfies this composition property. So let me write it again here. So this satisfies this composition property. Okay, I'll call this 2. Now, if we, in this expression, let us say that we set T3 to be equal to T1. Okay. We can do that, right? We haven't, even though we normally think, well, time has to have a certain flow in a certain direction. In this case, we haven't really said that, well, this is time. This is just some parameter, right? Psi is some function of some parameter T. Okay. So as far as just the formal mathematics is concerned, there is really nothing, we can always, instead of writing this as T3, we can write this as T2 and this as T3. And then we can reverse these two arguments. So this becomes U of T2, T3, right? So if we put T3 is equal to T1, then what do we get? We get U of T1 from the left-hand side here. This is T1, comma T1 is equal to U of T1, comma T2 and times U of T2, comma T1, right? So now what is U of T2, T1? This is the operator which takes me from psi at T1 to psi at T2, right? What will be U of T1, T2? U of T1, T2 will be the operator which takes me in the opposite way, right? So if you think of this as time evolution, then this guy is forward time evolution. And this one is reverse time evolution, reverse or backwards time evolution, right? So you can make your clock run in one direction or in the other direction. If you reverse the direction of your clock, what happens? How do you express that? Now, this guy, let me put it here. So we have this condition. Get this a little bit more clearly. T1, T1. Now, what is U of T1, T1? That is just the identity operator, right? We saw that here. This is the identity operator. So this means that U of T1, comma T2. What is U of T1, comma T2? It is what takes us, so to speak, back in time. Okay, is going to be the inverse of T2, T1. Okay, so the operator which takes us forward in time and the operator which takes us backward in time, they're related to each other. How? They are the inverses of each other. And it makes sense, right? Because if you want to go forward in time and then back in time, then you should come back to the same place you started from, right? From the same state you started from. So if going in one direction involves some transformation, then going in the reverse direction should involve the opposite of that transformation, the inverse, right? Which undoes that original transformation. Okay, so we'll call this 3. Now we remember this property of these operators. These operators, we require them to be unitary, right? Well, that is a requirement which just comes about because we want to say that the total probability of all the outcomes adds up to 1, right? Probability should be conserved. So if this guy is the inverse of this guy, then I can write u of t1 t2 as u of t2 t1 Hermitian conjugate, right? So this is from the unitary property. I get this result. Okay. All right. So now, okay. So now let me write down again our original expression, which was this guy. But instead of writing T2, I'll just leave it as T, right? So we want to understand the time evolution of this state from an initial time to some final time. We don't know what that final time is. It could be T2, it could be T3, right? And now we take the time derivative. We take the derivative of this both these sides with respect to T. So we can write d by dt of psi of t, right, is equal to d by dt u of t comma t naught, okay, times psi of t naught plus u of t comma t naught d by dt of psi of t naught, okay. But now this psi of t naught, that is the state at a time t naught. T naught is fixed, that is the initial time. So this time derivative will be 0, right? This state is not, I mean, it is our initial state. We can't change that. So this is 0. So we are left with this expression, right? Now this expression, what do we have? On the left hand side, we have the time derivative of psi, right? On the right hand side, we have the time derivative of some operator multiplied by the state at some initial time t naught, okay? But what we want is an equation which looks like this. What is this equation? This equation tells me that this Hamiltonian acting on psi at the time t is equal to the time derivative of that psi at the same time t. So this is an eigenvalue equation, if you remember. So in an eigenvalue equation, you need to have the same vector, the same state on both sides. So we have the state psi of t on one side. We want to put psi of t on the other side. How can we do that? Well, you remember that we have the notion of going backwards, right? So we can start from psi of t and go back to psi of t naught. And that means we can write psi of t naught as u of t naught comma t psi t. So this is the backwards time evolution. Okay. Again, please note that here our sense of what is forward and backwards in time is an arbitrary thing. It's up to us, right? So we have chosen, we have said that, well, when t increases, we are calling that forwards time evolution. But we can always say that we can take the other choice. It will not, we can say that if t is decreasing, it's some decreasing parameter going from minus infinity to infinity, then that is our quote unquote forward time evolution. We can always say that. So it's a optional thing. So we take this expression and substitute it in here, and we get d by dt of psi t is equal to d by dt u of t comma t naught multiplied by u of t naught comma t times psi of t. Okay, so now on both sides we have psi of t. On one side we have, this is some operator, let me call it O. This operator is acting on psi of t, and on the left side we have d by dt, the time derivative of psi of t. So this is our equation. This is our differential equation for the quantum state as a function of time. Okay, this tells us how the state evolves as a function of time. What we need to figure out now is what is this operator? Oh, what is this guy? Right? If we know the form of this operator, then we can solve this and we can understand how the system evolves in time. Okay, and you can see that this expression has the same form as our original Schrodinger equation. Okay, I guess I should put this on the left over here. Okay. Right? On the left side, we have the time derivative of the state. On the right side, we have the state and some operator acting on it. The only difference is that we have this coefficient IH bar. So if we look at these two expressions, we can see that these two expressions are the same if we choose to define our Hamiltonian to be equal to 1 over IH bar times this operator O. Okay. So in other words, the Hamiltonian for our system is equal to 1 over IH bar, that can be written as minus I over H bar times this operator.
Won't it be multiplication rather than division?
Sorry?
So won't Hamiltonian operator be iota h times O? Because we are
Yes,
multiplying iota
yes,
h bar to the
you're
both
right,
sides.
you're right, you're right. Thank you so much for that. Yeah, IH bar. Okay. So basically we have derived the Schrodinger equation. All right. So a lot of places you will see people say things like, well, the Schrodinger equation doesn't really have any derivation. And the answer to that is that no, it does. This is the derivation. Okay. But there is a lot more to be said, right? We have not, because the main, so also in this equation, I can replace this u of t naught t by u conjugate t comma t naught. So this is the final form, right? Because because, well, this guy is the inverse time evolution, so I can use what that property we talked about, right? So this is the Schrodinger equation. You can apply the Schrodinger equation. Now the thing is that you can either use this to solve for this operator u, or if you know the operator u, you can use it to solve for h. But normally what we do is we have the form of h already given to us. So as an example, one of the forms of the h, or this h operator, is for continuous quantum state, it looks like this. This is for the continuous case, right? For the discrete case, as an example of the discrete case I talked about, a particle in a magnetic field. In that case, it looks like this: minus mu naught b dot sigma. This is a discrete case, right? So depending on your system, you can use the appropriate Hamiltonian operator, and you can solve this equation. Now, in many cases, we cannot solve this equation analytically. It cannot be solved exactly in closed form. So we have to use numerical methods. But the point is that it can be solved. Okay. So we have talked about the time evolution which occurs due to this operator in the discrete case. Now, there is there is one more thing. Let me talk about that. So since this is an operator, right? H is some operator, right? Right. Now, since it's an operator, any operator will have some eigenstates, right? What is an eigenstate? An eigenstate, well, it's just the solution of this equation, where H is the operator on the left, and E is, what is E? E is the eigenvalue. Psi is the eigenstate, E is the eigenvalue. And this eigenvalue, what is it? It's generally some complex number, right? But now if you look at this equation over here, this expression for the Hamiltonian, okay? And you ask, what happens when you take the complex conjugate of this Hamiltonian, right? The adjoint of this Hamiltonian. So you will find that this is equal to itself, right? Exactly. So this means that H is Hermitian. If H is Hermitian, this implies that the eigenvalues of this operator are real numbers. We have talked about this in class before. All right. So what if we have a state like this, right? This is an eigenstate. Now I'm putting a label E on the state psi to indicate that it is the eigenstate corresponding to the eigenvalue E. What is this E? This E is the energy of this eigenstate, right? Because if you remember, that the Hamiltonian is equal to the total kinetic plus potential energy taken as operators, right? So what should be this quantity? This quantity is the energy, right? That is what this is. This is the energy operator, right? So if we have the position operator, what are the eigenvalues of the position operator? The eigenvalues of the position operator is position. Eigenvalues of momentum operator are the allowed momenta of the system. These are the allowed energies. Okay. So now we can ask, what if the system is in an eigenstate of the Hamiltonian? What is the time evolution of the system? So let me write down the Schrodinger equation again. Psi of t. But now I'll put a subscript E over here to remind me that I'm talking about the eigenstate of the Hamiltonian. So now, since this guy is a eigenstate, I can write this expression on the right as E times psi of E. Okay. Now what happens to this equation? Now this equation becomes an ordinary differential equation. Because on the left, what do I have? On the left, I have I h bar d by dt of psi of E t. On the right, what do I have? I have some number multiplied by psi of E t. I can write down the solution of this equation right away. The solution of this equation is exponential of minus I E t by h bar times psi of E at some time t naught. So what this tells me is that if I have an eigenstate of my Hamiltonian operator, then it only changes in time by some phase factor, e to the I theta t. Okay. Now, this is interesting because if you look at, we talked about that time evolution of this state phi of t, and we saw that this state phi can be written as a superposition of alpha acting on 0 and beta times 1. But this expression is not just a simple phase factor multiplied by the state, right? The reason is that this 0 is an eigenstate of H, this 1 is an eigenstate of H. So if you start in the 0 state, you will continue to be in the 0 state. And if you start in the 1 state, you will continue to be in the 1 state. So this answers the question that people had when I talked about this problem. They said, well, what happens if to begin with beta of t is 0? If beta of t is 0, then it continues to be 0. The state will remain in the 0 state. So another way to say this is that eigenstates of the Hamiltonian are stationary states. They don't evolve, quote unquote. They don't evolve in time except by a phase factor. Okay, I'll leave it here for now. I think this much is sufficient. We have derived the Schrodinger equation. We have talked about eigenstates of the Hamiltonian, and we have shown that the eigenstates are stationary. So there is a question in the chat that I talked about anti-unitary operators. So, well, an anti-unitary operator is so a unitary operator is U inverse is equal to U complex conjugate, and an anti-unitary operator, there is a negative sign. Okay. And similarly, I can talk about anti-Hermitian operators. So an anti-Hermitian operator, the operator is equal to the negative of its own Hermitian conjugate. Okay. All right. So this is the thing. All right. Any questions? Okay. All right. So I'll send the fourth homework set problems to you guys today. Okay.